Hello everyone and welcome to our Digital V-Days. My name is Markus Eberle and I will moderate this webinar session today. I'm very happy to welcome all of you and also to welcome our referent, Lorandt Fölkel. Lorandt, hi, nice to have you here.
Hi Markus, nice to see you as well, and hello my friends of electronics.
Perfect, thank you. So I'm very curious about the topic today, which is about how to select the right ferrite bead for filtering DC-DC converter. So I know it's about sound or noise today, noise, probably not the noise from a youth punk band, more about EMC. I know from my years or my experience, I had an old clock radio, and yeah, when my smartphone light next to it, it makes curious sounds. Hopefully, after this session today, I know how to solve this problem. Yeah, we will see.
Yeah,
Okay.
Markus, that was the old techno sound, the beginning of the techno electronic sound. Yeah.
Exactly.
Let me see if I have a chance to advise electronic designer how to avoid such kind of noise which is produced from the power supply.
Yeah, thank you very much. Okay, Lorandt, stage is yours. Have fun.
Thank you. Thank you so much, Markus. Yeah, ferrite beads, many people don't like them because they are tiny, they don't have a big suppression sometimes, but it is really important how to select the filter, and the filter is not just one component. So first of all, let me see if I can start my presentation. Here it goes. So what we can do for a good EMI. So we know that every DC-DC converter, they make some noise, input noise, radiated noise, output noise, depends on the topology. We have to pass the EMI, we have to pass the EMC test in the AMC lab. So first of all, we have to perform a very good PCB layout. The most important design tips what you can get all the time, it is when you are designing something, take care of your grounding. You must have a good grounding. You can put tons of ferrites, you can put tons of capacitor inside. If you don't have a good layout, PCB layout with a bad ground, no component will help. And sometimes you have just a scope on your bench. It's good if you have a good scope with a good FFT. If you have a very, very good scope with a good FFT, it can be sometimes very helpful, but I always prefer to have a spectrum analyzer as well. So if you have a good bandwidth, at minimum 1 gigahertz bandwidth, and you have a good FFT, you can find some EMI and you can try to redesign to find the right filter, but I prefer always to have a good spectrum analyzer additional. So what we will talk about today, we will talk about the 100 watt buck boost DC-DC converter, which need to be designed by 100 watt to be 95% minimum efficient. It must pass all the EMC tests like radiated emission and conductor emission. It must fit sometimes in a defined box because the marketing decide for you where have to put this design. So the marketing department already sold your design before you even think about what to have to do. So that's the reason why you have a defined box. And if you have a nice customer, like in this example, maybe they will request from you to make different, I would say, a suggestion, like one design should be low cost possible because it will be top millions of products. A second design maybe you will have because some people will say, okay, you should find a compromise, not too expensive, not too cheap, but must have some benefits and in performance, of course. And the third one, that's the best thing if you design from somebody who say, hey, I have budget, no problem, no budget limit for your DC-DC converter. Believe me, I never had this luck. So I always had a small budget and I always have the most high-tech requirement for that. But maybe you're a lucky guy and you will have sometimes low budget, no budget solution. So let me start with the selection of the IC. I always start when I select the DC-DC converter, I start with selecting the controller. And this is the LT3790, because if you look on the datasheet from this LT3790, an analog device, you can download the datasheet. You will see that the efficiency, it is almost above 95%. Depends on your input current, and we will have a request for input from something like 12 volt to 24 volt, and we need this 20 volt and 5 amp output. So it looks that this IC will be the good solution. The next step, I will start to design with a low-cost version. So the design A, it is a lowest cost version. It means a double-side PCB will not work, because in the same box I have to put also the DC-DC converter, and also I have a logic board which have a different package of the processor, and with 2 layers it will be impossible to route. So I will go by minimum 4 layer. Not because of the DC-DC converter, because of the logic board. So by 4 layer, to save some money, I decide to put components only on the top side. No components on the bottom side. I will save some money by pick and place, because it will be planted only on the top side. By the 4 layer, I have the possibility to use multiple ground layer for my DC-DC converter, which is quite a good benefit. And because I need to save space, because by 4 layer I need a lot of routing for my QFN package, I will start with a higher switching frequency, which is 600 kilohertz. At 600 kilohertz, I will use the smallest inductance and the smallest capacitors. Like you can see, I will use also some kind of gate resistors, 1 ohm input capacitor, output capacitor. Because it's buck boost converter, I will need some MOSFETs as well. For the MOSFET, the decision was on Infineon, because the Infineon MOSFET request, the requirement is it's okay. It can handle 60 volt, it can handle 100 amp. Efficiency estimated by the calculation 95.5 should be quite okay. The package is not the best one, because it has quite higher thermal resistance and have also some not optimal resistance, thermal resistance, quite high ASL, but okay, the price is good. The components will fit to my decision. Now for the inductor selection, you can try to use our online tool, which is the Red Expert. I will show you how to select the Red Expert if you know the parameter. So I will switch now to my Red Expert. So if you go to our website, here's my mouse here. So if you go to vonline.com and then type Red Expert on the link directly, it will open the Red Expert welcome site, and you can decide here, you can calculate different components, capacitors, filtering, thermal management, but I will go to the DC-DC converter selection. I will calculate first the buck conversion, and in a buck conversion I know my parameter. It will be like, double check again, I'm on the 14 volt input, 20 volt or 18 volt output. So I will put the same 14 volt minimum input, 18 maximum, and output 5 volt and output 20 volt and 5 amp. The switching frequency 600 kilohertz. Delta ripple inductor. Okay, in this point you can already decide how good your efficiency could be, how small the inductance can be, or how big the inductor could be. Because if you go with a ripple current more like 50% of your nominal current, you will drive a high loop in the BH loop in the magnetization, and you will have a lot of ripple on output, and you will concentrate the maximum losses into the core losses. If you go below 10% ripple current, you will have a small BH loop, you will have a small magnetization. The inductor will be big, but the ripple, output ripple, will be very small. A good starting point is, I would say, somewhere in the middle, 30%. So not above 40, not below 20. This is a good range for the calculation. And I will go here to the show suitable. I say update, and then automatically select all the components which it's not fit to my requirement is outsorted. Now we know we will have here a peak current of 6.2 amp. So this is very important to take care about this, because if you go above this current with a saturation, and the saturation is less than 6 amp, you may have this problem that the inductor will saturate, and the triangle in the graph that you see here, the current flow, it will make spikes, and spikes is not good for EMI. Spikes is not good for the lifetime of the components, also as well for the MOSFET and so on. I will take care that the peak current should be less than the saturation of the inductor, and take care about the saturation of the inductance, because there is no standard definition for every manufacturer. Every manufacturer uses different standards. So in our decision, we will say 10%. Above the 10% saturation, the inductor start to be saturated, is not a good behavior. So I will choose something which is less than 10% in the saturation. So what I need an inductance something by 4.4 microhenry. So I need something more like 4. If I choose this component, as soon as I select this component, it tells me it has 44 Kelvin temperature rise. It means if I have 20-degree lab condition like here in this room, and I put this current, it will rise plus 44 additional temperature. So 20 plus 44, it will have 64 Celsius on the component. This is too hot for me. If you can touch it and it feel warm, it's good. If you touch it and it feel hot and you take your finger back, that's a sign it's something wrong. I don't like that. This is the cheapest thermal camera actually for myself. I will not choose this one. How about this one? 28, that looks a little bit better. Why? Because I have only 28. So if I have an ambient temperature of 85 degrees plus this 28, I could survive 125. Maybe I should choose a high temperature version one. Oh, that's great. I like that one because it's only 15 Kelvin and it can go up to 150 degrees Celsius. With this one, I will be more like happy. It have 3.3. Okay, this is, I need 4.4. I need another one. Maybe I should choose another one. How about this one? 33. How about this one? 60. Oh no, that could be too hot. 24, that looks better, so I will like this one. Now, if I compare this with the other one, you see the inductance behavior. Here, the inductance is linear, it's quite very good. It's quite very good, and now it starts to saturate, and then it goes very fast down. This one has a linear saturation because that is a alloy, and this is a ferrite-based one, so I will skip this one. And to compare with something else, how about this one? I will compare with this one. Both looks quite similar, just behavior of the saturation, it's like that. One is getting more hotter, the other one is gets less hotter, of course, because of the DC resistance and of the size. But what is more important if we take care about the saturation point? I will make this a little bit bigger to have a better point. So we know that both looks in the ambient temperature quite very nice. What will happen if I have an inrush current for short time? I have actually a 5 amp nominal current, which is not that bad. But maybe when you switch on, it's an electrical motor or engine, or maybe it's a computer which is by first impulse is sucking too much current. It can be make an inrush situation, and the current or the saturation by, if you exceed something like 10-12 amp, maybe I would say, okay, in this situation you will have only maybe 7 amp. It looks by blue one, if you select the blue one, quite okay. The yellow one, it's not a big difference. It doesn't happen too much, but all these curves, what you see, it is also in the data sheet. This is measured at 20 degrees Celsius. What will happen if I have a hotter ambient temperature, like maybe you will have an ambient temperature something like, let me see, 100 degrees Celsius. At 100 degrees Celsius, look what will happen. Did you check? The 7 amp at 100 degrees Celsius, by the yellow one, it will drop to 3.7. The DC-DC converter will still works for just by switch on by this inrush, but the blue one is already dropping to, wow, 1 point something. I don't believe that this will still operate. So I will not go with the blue one, for sure. If you go to the minus degrees, like, I don't know, maybe if you will ship that to the North Pole or Antarctic, the South Pole, you see that at minus pole, it's not a big issue. By minus, the saturation, it's a little bit later, which is an advantage. But at high degrees Celsius, I will not go with the blue one, so I will stay with the yellow one. This is my selection. With this one, I could survive also in laboratory condition, and I will survive also in higher hot temperature. So that would be my selection in this case for the first step. I don't have a high temperature rise. I have 125 degrees Celsius operating temperature. I have shielding. I can see the temperature rise. What will happen if I have a short circuit, like maybe the fuse is like an 8 amp fuse. At 8 amp fuse, I would have 35 Kelvin self-heating. Okay. What is the behavior if I use that for filtering? I can see the impedance curve. All this information is given a Red Expert. So please choose Red Expert if you select inductors. This is the easiest way, instead of using a lot of calculation and don't know what happened in real. So I will go back to my PowerPoint. In this PowerPoint, I did choose a different component. I choose a HMI. And this HMI, it was chosen because I have a delta T of 16 Kelvin. The total losses, AC losses and DC losses, by the way, the Red Expert is calculating by the AC losses, not only just the core losses. It is included also the skin effect losses, also the proximity effect losses, so it's not only core losses. And we don't use a Steinmetz formula for that, because Steinmetz formula is valid only if you have a 50% duty cycle, and in our calculation it is not a Steinmetz formula. We have our own algorithms, and it is included much more and much accurate. We are 99% correct according to the measurements. So all the data what you will see in the Red Expert are measured actually data. Now we know we have a peak current here of 7 amp. I did choose something wrong. I was maybe a different voltage, I guess, and that was the reason why we have 7 amp here. The saturation here is 13 amp. It looks 27 amp. Oh, far away. It's very good. So we have in boost mode a quite good selection. In buck mode, now it's buck mode, we have again a 16 Kelvin rise because of the AC and DC losses. The DC losses is because of the DC resistance of the wire. The same component, it looks good. Peak current 5 amp is below 27, more like enough. That's a good choice for my inductor, and that looks like that. So this is by 30% ripple current, a 4.7 microhenry inductance, size 10 mm by 10 mm. It's not so big. DC resistance 5.4 milliohm. It's quite excellent for my DC-DC converter for the low-cost version. Now for the input capacity, of course, by the 600 kilohertz, I would expect that I have not more like 100 millivolt peak to peak on input noise. So to this calculation, I will need 14 microfarad in this case and maximum current. I would go by 4 times 4.7 microfarad in this case, because I don't like to concentrate all on one single capacitor. I like to put capacitor and input and also an output in parallel, because if you put capacitor in parallel, you put resistors, because I have ESL and ESR, resistors in parallel, so we'll eliminate some of resistance, you eliminate some of the parasitic inductance as well, and I will decide to go by 4 times 4.7 microfarad, because if you have to include also the DC bias drop of the capacitors, which is again in the LED expert to find, you can see what will happen if you have 24 volt. You will have on this capacitor a drop of something like 20%. So that's the reason why I like to put more capacitors in parallel. The same thing you can simulate in LT Spice. You can take the jig from LT Spice and you can simulate that, but please use for the simulation not ideal components. Use components from the library, and if you choose virtual electronics capacitors and virtual electronic inductors, you will see that we include the parasitics, because inductor alone, it doesn't exist alone. It's always a LCR in parallel. We have parasitic resistance, we have parasitic capacitance. The winding capacity, it is there. You cannot avoid that. If somebody tried to sell you an ideal component without parasitics, that's voodoo or maybe some black magic, I don't know, but it's always you have parasitics. Capacitors, never exists capacitor which is infinite, goes to the deepest insertion loss, impossible. Every capacitor have a ASL, parasitic resistance, and parasitic ASR and parasitic inductance. So it's always LRC in serial. Please include this in your simulation, else you will cheat yourself. Even PCB tracks, if you put PCB tracks like here in my simulation, if you include the PCB tracks in the crucial areas like here the switching nodes, if you put that 1 nanohenry per millimeter PCB track, you will have a more accurate simulation. And if you look to the simulation here on the of your picture, if you look to the screen, on the left hand you will see the simulation, and on the right side you see the measurement of the scope. You can see that both are very close to each other, so the simulation is quite very accurate because you include all the parasitics. Now if you make a FFT calculation on this noise, like this is the input noise, you will see you have to put a filter here for sure, because in buck mode the DC-DC converter will generate for sure some noise. And now if you take a listen, you make your own listen, you do it yourself listen, it's also possible to do that. It's available also on some website like Electro, you can download, and you can also build your own listen. And you take the listen and you make with the FFT from the scope a nice spectrum. You can see this is my input noise, and you have to do here something to achieve the EMI requirement, which is something, the level, it is here manual, because on this RTO was not possible to load the limits of the standard 55 or 25. You can see here is the limits, quasi-peak and averaging. Scope doesn't have quasi-peak detector. It's also an EMI receiver need, but you know that the limits are there. And then you can see we need to build a filter which has at the maximum peak something by 90 dB microvolt. To achieve this minus 40 dB line, you need a damping of minimum 50 dB in this case. So our filter must be better like 50 dB to be able to eliminate this noise on the input. So this is how we did measure. This is actually in our EMC lab. We have this scope, the RTO. We did use a listen from Langer Electronic. It's very important that you have always this ground space. You have this ground plane where you put your devices. The load is just a passive resistance load, and when you measure the input noise, you will have some issue to fix it. If you have a spectrumalizer, you can measure much more precise and much more efficient and better like a scope with a FFT. It's possible to have a good scope. If you have a good Roden-Schwarz scope, you have quite very good FFT on that, a very high accurate. You have to use a lot number of bins, and then you have a good transformation in Fourier. So what we have to do now for the DC-DC converter? First of all, we will have two stages. We will have one in buck mode filtering, and we need to filter the boost mode as well. In boost mode, the noise is not on input, on output. by using the buck conversion. In buck mode, you don't need to focus on output. You have to focus on input. In input will have the most noisy area, and in boost mode the output will be the most noisy area. So actually we need an input and an output filter. The simplest filter what you can do, it is like a T filter. You will use an inductance, a capacitor, and a ferrite bead. The input capacitor is always there, and we will put another electrolytic capacitor on input, because by the measurement we will measure only the DC-DC converter alone, and with this cable which is on the input, these cables are also inductive and they will generate also high peak, and we don't want to kill the IC with the over voltage. So that's the reason we will put a bulk capacitor on input, a bulk capacitor on output, only just for the test setup, not for the final design. So filter for input, we can start with a simple T filter. We can optimize this, the different components. You can see here, this is the simulation file for the input filter, output filter, and compare it just with the LC filter. Just using a LC filter, we will see in the simulation file that the LC filter doesn't have enough efficiency to achieve this 50 dB insertion loss. You will need more like a LC, you will need a T filter. We will decide to use, because of this reason, a good T filter for input and another T filter for output, because I'm afraid the output will be more noisier by boosting and it less noisier by input, and that's the reason why the input filter is a little bit less efficient like the output filter, and this is not the same 100%. This is both of them because of the switching frequency. And additional we will put, because we will measure the DC-DC converter with wires. It means output wire to the load, input wire to the listen. These wires can act like an antenna, and when we want to measure that in the anechoic chamber for radiated emission, I'm afraid to have these antennas, and that's the reason we put a common mode choke on output and we put a common mode choke on input. This common mode choke cut the antennas. This is only just the reason by the radiated emission. We could avoid the second common mode choke if we put that in the box together with the logic board. Maybe we will not need that. Who knows? We will put there. By the measurement, we will find out if we need or not need. I'm almost sure the input will be necessary, because the input, it will be also generate some common mode noises, and this common mode noise need to be filtered. So that's the reason I am almost confident that the input common mode choke, I will need that. So I will choose a 56 microhenry most bandwidth with 7 amp input, and I will use a 120 microhenry in inductance for output common mode choke. My current is 5.5 maximum rated current for the common mode choke. It looks fine. I will use that combination. So this is the final schematic now for the design A. 4 times 4.7 microfarad input, 4 times 4.7 microfarad output for a DC-DC converter, the input T filter, output T filter, and the common mode chokes, and this 1 nano capacitor for ESD discharge, just for be safe. Now we have the design A. Start with the design B. Design B, it's a compromise. Design B, it is not too expensive, not too cheap. So let me go by the 6-layer PCB. I will change now from 4-layer to 6-layer. By 6-layer, I have the opportunity to have 2 ground layer and close between 2 ground layer the noisy area. Now I can put components on the top and bottom because it's more expensive. I can spend some more money. I can reduce now the switching frequency to 400 kilohertz because I have more space now for routing. I have many possibilities, and I will skip the 1 ohm gate resistors. Now for the MOSFET, I will change to the from Infineon to the Texas Instruments one. Has a much better package, has an extremely small ASL, RDS on is very small, very good thermal resistance, cost a little bit more, but it will be paid back. Again, I will calculate with the Red Expert the 400 kilohertz inductance. It will be 6.8 now decision, 14 Kelvin in boost mode self-heating, 14.7 self-heating in buck mode. I will choose in the same family. It will be the same X HMI, it will be 4.1 milliohm. This resistance, because the package is now from 10 by 10, it will be 15 by 15. It's still excellent to my decision. The input capacity, again, because I will go now about 400 kHz switching frequency, I will need to increase the capacity to achieve this 100 volt peak to peak. So according to the DC bias consideration, I will need something 21 microfarad calculated. If I put 4.7, I need to put, instead of 4 pieces, I need to put 6 pieces. X7R dielectricum, 20% drop, 23, it looks quite very good. Excellent in the expert to calculate. Now, the input filter, how is calculated? How the decision made? So first, we have the input capacity with the inductor together. So this is the first stage of the filtering. Then we have a ferrite bead. We have another ceramic capacitor. Then we have the common mode choke, and we have the 1 nano capacitor for this ESD discharge. This common mode choke is responsible for 30 MHz, 300 MHz. The next ceramic capacity with the ferrite bead is responsible for the 5th, 7th harmonics, and the electrolytic capacity, actually it's a polymer capacitor with the inductor, is responsible for the lower frequency 100 kHz to 5 MHz. Take this input filter and mirror to the output, same decision. Now, this is the calculation now, simulation for LT spice. You can see here we did choose the MPSB ferrites because it has a better pulse testing, and also the inrush current. It looks much better. We have input-output filter component simulated. We saw that we have more like 50 dB insertion loss. This is my schematic now. Instead of 4, we have 6 times capacitors, and we can go to design C. Design C have no budget limit. Design C no budget limit, it means I can use 24 layers. Nah, make no sense. We can keep the 6 layer, was more like enough. The one thing what I can do now, I reduce the minimum switching frequency to 230 kHz. I would achieve now the highest inductance value and more capacity on input. But because of that, I will skip the gate resistors, and I will use a little bit different filter like before. I will use the same MOSFET. The input and output filter, I will decide to redesign a little bit. For the inductance, I will choose, of course, one which has just 5 Kelvin self-rise. I want to have the best efficiency in this case. This is in boost mode. This is in buck mode, looks excellent. Of course, the inductor will be now huge. It is something by 28 by 27. Has a DC resistance 1.3 milliohm, extremely good. The inductance value is 10 micro by 230 kilohertz. I'm very confident I will have the highest efficiency with this one. The frequency is so slow, I will expect maximum 20 millivolt peak to peak at 230 kilohertz. I will need 186 microfarad, so I will use not 6, I will use 7 4.7 microfarad capacitor. I will put additional 220 microfarad polymer capacitor, additional parallel to MLCCs. So I will have a good input filter capacity. For the input filter, I will skip the inductor. I will leave just the ferrite bead. Same for the output. I don't need it because my frequency is too slow. I don't afraid about that. And that's my final decision. You can see skipping the inductance and output and input, put lot of input capacity, lot of output capacity, more like enough, looks excellent. Now we have all 3 boards made, and then we go to the EMC lab because the EMC lab will take the decision which design is the best. So first of all, we start with the design A without filter. You can see here it is directly connected to the wires, and no filter input, no filter output, and the 600 kilohertz make a lot of noise. We have the according to the CISPR 32, we have the quasi-peak and the averaging, both are exceeded. We need a filter, so we switch on the filter, and quasi-peak maybe is good, but averaging is not good enough. I need to redesign the filter or rethink my design. But it looks quite very good here. It means if I have below average, maybe I will pass the radiated emission. And let's go to the radiated emission chamber. Without filter, it doesn't look so good like expected. I will need a filter anyhow. So if I put the filter on, like expected, at least the radiated emission, it could fulfill more like 10 dB distance. I am more confident that this one is a radiated emission, no problem anymore. Now, let me take the design B. Design B, without filter, 400 kHz switching frequency. Without filter, I can see in comparison with the 601, I am already here quite very good. No filter connected. Let's connect the filter. If I connect the filter, whew, I'm good. By first shot, design B passed the conductor emission, quasi-peak and averaging. And let me see how it looks in the anechoic chamber if we test the radiated emission. Radiated emission without filter, yes, like expected, it is below the limit. I will come back for these peaks, 130, 180 and 380 megahertz. But without filter, I will not pass conductor emission. Let me switch on for the radiated emission, also the filter on. And now with the filter, we are below the limits, more like enough, looks quite very good. First shot, conductor emission done. First shot, radiated emission done. Think about yourself. How often happened to you that you passed the EMI test by first shot? This is lucky punch, I can say. This is almost lucky punch. Okay, let's see where it's coming that this peaks of the receiver. So if you go to the switching node and you look on this overshot and ringing, and you make a FFT on this ringing, you can see exactly 130, 180, 380 megahertz what the receiver sees. So what you have to improve in this case, try to avoid this overshot, try to make the ringing small as possible. That will be helpful also in the EMC chamber, and you will pass the radiated emission much easier. Now, if you look on the design C without filter, again measured with the biggest inductor, you can see that the 600 kilohertz switching frequency making the, I would say in the this is 1 megahertz, 2, 3, 5, 6, 10, something like here. So here in this area above 5 megahertz, it's almost no noisy. So you don't need an excellent filter for radiated emission in this case, because radiated emission start at 30 megahertz. But let's switch on the filter because we need to pass conductor emission as well. Not so lucky punch this time, because I still have the 230 kilohertz and the third harmonic, because maybe I should not skip this inductance. My decision to skip the inductance was not so clever. I have to put back and skip maybe the common mode choke. Because if I go now to the radiated emission chamber without any filter, without filter, without common mode choke, I already passed the radiated emission. I don't need more like 20 dB. I have here more like 10, 15 dB distance. So I'm more like enough. And now should I switch on the filter because I have to pass conductor emission as well. And I can see here on this peak, which was not there before, that this peak here make a little problem. That's a sign my filter is oscillating. My filter is ringing with a noise. I have to redesign this filter for sure. Maybe skip the common mode choke on one side or both sides maybe. And I have to rethink the filter. Anyhow, I have to put this inductor back, and else I will have a problem. It's below the limit, but I don't like to have filter ringing. This is always a bad sign. So if we make some measurements directly on the components, we can see that the voltage on the gate source on the A design and the design B is totally different. This is because of the layout. The layout is different, 4-layer to 6-layer, and also the MOSFETs are different because of the ASL. This is the sign which you see here in this area. Exactly here you can see, maybe I should change that. Here you can see exactly here this ringing. When you switch on this ringing, this is the EMC noise. Please avoid such situation like that. This is bad EMI. If you look on the H-field probe, if you take a H-field probe and you go close to the inductance, you will see that the inductor is no, because it's shielded. All the inductor was shielded version. And if you go to the PCB track on the high side of the MOSFET, you will see this is the PCB track which you have to pay attention. This track should be not auto-routing. This track should be manual routing and should avoid to build antenna or routing in the different layers. Now, the bootstrap on design A and bootstrap design B, again, is big difference, because you can see the noise on the design A. It's the layout. For sure, it's layout, and also the other diodes. If I choose another diode in design C, which I don't tell you, it's improved a lot, the bootstrap. And this is the reason why you should put a ferrite bead on the driver, on the gate driver. If you use a IC which have an input for the gate driver, you should put a ferrite bead, because this ferrite bead can make sometimes really wonder. You can see this is the switching node. Exactly, here is the switching node, and if it's a 0 ohm gate resistor, just use it. Or if you use a 16 ohm or 2.2 kilo ohm ferrite bead or 600 ohm ferrite bead, it will improve a lot your EMI. This is the EMI measurement on the same design, just using, instead of the gate resistor, we put this ferrite bead on the VCC input of the IC for the driver, and that is a lot of improvement in the high frequency. Now, you want to know the best filter design. I'm sorry, it doesn't exist. Depends on the situation, you have to tune your ferrite. You have to tune your ferrite, you have to tune your filter. I would always think like that. I have an input capacitor. On the input capacitor, to the adequate capacitance value, I have to think about this inductance behavior. So you cannot put here a very high impedance or a very high millihenry inductance, because this ferrite bead is acting like an inductor, and he will slow down the current. So you cannot put a maximum more like 1-2 microhenry inductance here, else the capacitor on input will die hungry. It won't be charged in time. This is the minimum, but you can put a small inductance. If this inductance is not enough, you can put another ceramic capacitor and you can put a small ferrite bead. A ferrite bead 100 to maximum 300 ohm. I never exceed 300 ohm ferrite bead. Normal, the ferrite bead's impedance, all the impedance is measured in the 50 ohm system impedance. We have on a DC-DC input of the converter, never 50 ohm. We have almost a much lower system impedance, so the source and load impedance in a system impedance, it won't be 50 ohm, never. So I would suggest to use first starting with something like 100 and look what's happened if I go up, or look what's happened if I go down with the impedance, but don't put 1 kilo ohm ferrite beads here. It won't be the right solution. Use small components, low ASL capacitor, low ASR capacitor here, and then this is responsible for the third harmonic. For the fifth, seventh harmonics is the next stage. This is my input. You can mirror all that to the output in the same way. It will be acting, it's a boost converter. If it's a boost converter, you don't need to focus on input. If it's buck converter, don't need to focus on output. If you want to avoid common mode issues, you have to use a common mode choke. Else you will not pass the radiated emission. Some little explanation what is the benefit of shielded, unshielded inductance. Both have a bobbin core with some wire, and the benefit is by having less radiation. This is a measurement just conductor emission without shielding. The same DC-DC converter with shielding. I think you can see by yourself that the peaks are less, and in the anechoic chamber it paid back by radiated emission. Use always for storage a shielded inductor, rule number 1. That's the best thing what you can do if you want to avoid EMI problems. More information you can get in these nice books. You can ask my colleagues or on the website, and please feel free to ask for a copy. If you want to be in touch with me, I have also a small landing page. If you go to the landing page of our website, or you just type Ask Lorandt in YouTube, you will find some crazy videos made in the laboratory. Thank you for your attention. I guess Markus have some questions now from you.
Yeah, Lorandt, thank you very much. It was very interesting, very cool testing and yeah, new things. So we have got a lot of questions also from you and we just want to start with that. We have a little short time for the Q&A, but if you have any or if any of your questions will be left afterwards, we will answer them by email. So we will answer all your questions. So first question. How much saturate the ferrite bead if I use a DC-DC power supply filtering?
Yeah, that's in fact something happens. So always take care not using a smallest component like O2, O1 or O4, O2. I would choose the maximum biggest component which is fit to my design. And if you want to know exactly how much to saturate, I can show you in LT Spice. You can choose in LT Spice the ferrite bead, where you can even simulate the ferrite bead saturation behavior. If you choose the model Z in bracelet I, this is a model for the ferrite beads from us, and we have these curves and just have to go and say, okay, add trace, and if I know the voltage, and I divide the voltage with the current. I don't want to see the phase. I have here exactly the impedance by 0 DC bias. This is a step parameter from 0 amp to 6 amp in a 0.5 step, and you can see the saturation happening quite very fast. I choose one ferrite bead which is quite very fast saturation because it's small, 0805 side. If you use a bigger one, it's also welcome to use a higher current as well. And if you have more ferrite, you have more possibility to put this magnetic field into the core. So
yeah,
it is happening. It's like a DC biasing of the MLCCs. It's also because the current goes and make a magnetic field, but as bigger it is, as less saturation you will have.
Okay. Thank you very much, Lorandt. Then we will hop to the next question. What is the maximum impedance if I put a ferrite bead as input filter?
Like I said before, maximum 100. I will never choose more like 100, 300. 300 is absolute limit. Very rare, very rare. Mostly a ferrite bead which is less than 100 ohm, it's quite very performant because the ferrite bead has less layer, and having less layer you have more bandwidth. So
okay,
never use more like 100.
That's a good rule of thumbs. Perfect. Are the ferrite beads shielded?
Yes, indeed. The ferrite bead, in fact, is nothing else, just air core put into the package of ferrite. So it has no gap. It will have saturation according to the big currents. So pay attention to big currents, but it's completely shielded. It's no escape of radiation.
Okay.
It's like a toroid.
Yeah. Thank you very much. So then next and last question due to the time. Can I put two ferrite beads in parallel if the current is too high?
No, time out. No. Never do that, please. Don't put two inductance in parallel by same current because it doesn't exist cloned products. Even if it's from the same lot, from the same machinery, you will have differences. And if you put two springs in parallel, it's very dangerous. I don't like that. If you don't have ferrite bead which is not withstand the current, use inductor, use a wired coil or something, a ferrite which is a ferrite rod core wire wound or something, but don't put ferrite beads in parallel. I saw one of the designer put 4 ferrite beads in parallel to check to fulfill the current needs of the input, and what will happen, it was after a while it was one is blowing up, then the second one, and the third one, and the fourth one. Actually it was a nice firework, but don't do that. Please don't do that.
Okay. Lorandt, thank you very much for your time today. And yeah, it was really a pleasure to have you here. Stay curious. We also have other webinars in our digital V-Days about component selection, about EMC. So just go to the website and yeah, and if any of your questions are left now, we will answer them by email. So then, thank you very much for your attention. Lorandt, thank you.
Thank you, Marcus. See you next time.
See you next time. Have a great day. Bye.